Today, we're going to crack a code. Seriously, we're going to take all those abstract numbers and letters you see in algebra and show you that they're actually a hidden blueprint for a picture.
So what if you looked at a math equation, something like y equals 2x minus 1, and instead of just seeing a problem you have to solve, what if you saw a secret code? Like a set of instructions for drawing a picture? I know, it might sound a little out there, but trust me, that's exactly what an equation is.
And that's our whole mission for the next few minutes. We're going to crack that code. We'll look at an equation, a table, and a graph. And you'll see they aren't three separate things at all. Nope, they're just three different ways of looking at the very same story. All right, let's start with view one, the code itself. This is the equation, and to crack it, we first need to get familiar with its key parts. Okay, first up, we've got variables. You usually see them as x and y. Just think of these as the moving parts of our code. Their values can change, right? And that's super important because that's what lets us create a whole picture, not just a single dot. Next, you've got the coefficient. That's the number that's right next to a variable, kind of like its boss. It tells the variable how much to scale up or down. So in an equation like y equals negative 3x, that negative 3 is the coefficient. It's a really powerful instruction in our code. And finally, there's the constant. This is the solid, unchanging number in the whole equation. So if you see y equals negative 2x plus 3, the constant is that 3. It's like our anchor, our fixed starting point before the variables start doing their thing. Okay, so how do we actually use this code? Let's take our equation y equals 2x minus 1 and find our very first clue. The process is really straightforward. First, you just pick any value for x. Let's go with 3. Now we plug that into the equation, so we get y equals 2 times 3 minus 1. A quick bit of math, y equals 5. And boom, just like that, we have our first clue, the ordered pair 3, 5. Okay, let's switch gears to our second view. We found one clue, which is great, but now it's time to get organized and gather some more evidence. I mean, think about it. If you're trying to figure out a picture, one single dot isn't going to tell you much, right? Is it a star, a circle, a straight line? Who knows? We need more points to really see the image take shape. That's actually why it's always a good idea to find at least 3. Sure, 2 points can make a line, but that third one, that confirms you're on the right track.
And you know what? The best way to keep all these clues organized is with a table. It just makes the whole process systematic. We can pick a few different values for x, run each one through our equation, y equals 2x minus 1, and just list the results. Look at that. Now we have a really solid collection of clues. Okay, now for the grand reveal, the really fun part. View 3, the picture. This is where everything comes together, where our abstract code and list of clues finally turn into something we can actually see. And here's the absolute key to the whole thing. A linear equation is just a description for a bunch of points that all line up. You know, the word linear literally has the word line hiding right inside it. It's been giving us the answer this whole time. So let's take those clues from our table and put them on our map, which is, the coordinate plane. Each one of those ordered pairs gives us an exact location to put a dot. One value for the horizontal x-axis and another for the vertical y-axis. Let's go ahead and plot them out. And there it is. This is the magic of it all. When you connect the dots, they don't make some random squiggle. They form a perfect straight line. That equation wasn't just some math problem. It was the actual blueprint for this very picture. In fact, every single point on this line is another solution to our code. Okay, that's all great in theory, right? But how does this actually show up in the real world? Well, let's take a look at a super practical example. Corey's day at the fair. So, the situation is pretty simple. You've got a one-time fee just to walk into the fair. After that, every single ride you go on costs extra. This is a linear relationship just waiting to be discovered. So check out this table. It's exactly like the one we made for our x and y equation. But this time, we have the number of rides and the total cost. If Corey goes on 0 rides, it costs $8. 1 ride, it's $10. 2 rides, $12. See? We're just gathering clues about Corey's day. So can you spot the pattern? What's the code behind these numbers? Take a second. You can see the cost starts at a certain amount, and then it goes up by the exact same amount for every single ride. And here it is. The code for Corey's day is cost equals 8 plus 2R. That $8 admission fee, that's our constant. It never changes. And the $2 per ride, that's our coefficient. It scales the cost up with every single ride Corey decides to go on. So, this really brings us to the big takeaway here. We've looked at abstract math and a real-world story about a fare. And you know what? The process was exactly the same. We're finally seeing the full story.
And that story is always told in these three views. First, the equation, that's the code, the basic rules. Second, the table, that's our list of clues that we find using the code. And third, the graph, that's the final picture, the big reveal. They're not different ideas, they're just different ways of telling the exact same story. So we've seen how these simple linear equations tell stories that move in a straight line. It's predictable, right? Which leaves us with one last question to chew on. If straight lines tell simple stories, like a constant price for a carnival ride, what kind of wilder, more complex, curving stories are being told by all those other equations out there?